Okay. So can you hear me? Hello?
Yes, sir.
Okay, so I am sharing this slide. So okay. So in the last class, we have developed the concept of the joint distribution, and through one of the examples, I gave you the idea that how the probabilities, joint probabilities are calculated, and ultimately, as you have seen that uh, we use the standard notation that probability x equal to x, y equal to y, and we put the subscript in a small p x y just to indicate the variables, random variables, and in the bracket the values taken by random variable x and y. So x correspond to small x, y correspond to small y. So if we change say w and z, then it will be here w and z, and then corresponding values could be anything. So it is the usual practice that the joint distribution is expressed in form of the bivariate table. So in the table, in one of the column, one random variable is represented, and in row, the second variable is represented, and we can also use the matrix form to represent the joint distribution. So corresponding row and column sum gives you the marginal probabilities of the respective random variable. So having done that, we have defined the conditional distribution. Say in general, probability of x equal to xi given y equal to yj. So we can write it in the form of the joint probability and divide by this, so that is equivalent to pij and p dot j. So yesterday I introduced the dot notation. Now again, uh, we may check that whether x and y are independent random variable is a random variable, uh, whether yes or no. So in that case, the concept of independence of the random variable is defined, and as we have discussed in the case of the probabilities of the a given b is equal to probability of a, then a and b are independent. So same concept is applied here. So as you can see that this, if this conditional distribution is independent of y, then it will be equal to probability of x equal to xi, and we substitute in this expression equal to probability x equal to xi. So it will come into this form. So if x and y are independent random variable, then their joint probabilities can be expressed as a product of the marginal probabilities, and it should be true for all I and j. So I took one example and showed you that in this case, you can cross multiply the respective marginal probabilities and see that the values are equal to their joint probabilities. So, but if any of the condition is violated, means at any place for some particular I and j, this Pij is not equal to Pi and Pj, then we cannot say that x and y are independent. So for independency, all Pij must be equal to respective product of respective marginal probabilities. So till this point we did yesterday. Now, sometimes we need to find out the expectation of the function of some random variable x and y. Say we could express our function in terms of x plus y or xy or x over y. So in most of the application, we need to find out the expected value of x plus y and expected value of x y. So usually the expectation of uh, any function of x and y, say gxy, is defined as double summation x and y, gxy, and product of the joint probability. So this is the general definition, and in fact, it is uh, it is true for any function of x and y. Okay, so this is an important result. And later on, you will see that in many cases we need to calculate, and I will take up one example to show you that how these values are calculated. So there is a simplification of this result. If gxy is x plus y, then what we can do, that we can find a simplified expression. So expected value of gxy, as per the definition, it is x plus y. So here we just substitute x plus y and multiply by the joint probabilities. Having done this, then what we do, we separate the terms. So x into pxy, y into py. So once it is separated, now if you look that, we just take x outside and sum over all possible values of y, the joint probabilities. So here we have uh, separated the terms. So see, in a similar way, the second term y has been taken out, and then summation over x, the joint probability is done. So since this particular expression, if you look that, we are summing the joint probability over y, and here we are summing the joint probability over x. So these two expressions gives you, this gives you the marginal probability of x, and this gives you the marginal probability of y. So x pxx, y pyy, and this we know that it is expected value of x, expected value of y. So in order to compute expected value of x plus y, though one can use directly this formula, but there is a simplified result which is more convenient than the previous one. So in general, expected value of x plus y is equal to e of x, e of y. So this is one result. Now the product. So when we have to find the expect gxy equal to xy, so simply we write expected value of xy and double summation xy and multiply by the joint probabilities. Say for example, in the previous example, if you see, we need to find out expected value of xy. So what we do, this is the x value, this is the y value. So 2 into 0, corresponding probability 0.06. 2 into 2, 4, multiplied by corresponding probability. 2 into 4, 8 multiplied by corresponding probability. So 5 into 0, 0.14, 5 into 2, 0.35. So like this, if you proceed, you can compute the expected value of x, y. So this is the general result, general expression for computing the expected value of x and y. However, this expression can be simplified in case x and y are independent. The previous result, when we computed expected value of x plus y, it is e of x plus e of y. It is true for all. Okay, but here in the case of multiplication, that expected value of xy, this is the only way you can compute the expected value of xy. Okay, so this is a general result. The special case of this is that if x and y are independent, then we can get a simplified expression. Otherwise, you have to use this result. to compute the expected value of xy. So let us see what is the simplified expression if xy are independent. So if expected value of xy, we can write xy into, since x and y are independent, so using because this is given, so we can write the joint probability as p of x and p of y. Okay, so now you just simplify because all the terms can be separated, and then ultimately you get expected value of x, expected value of y. So we can use this result to compute the expected value of x into y if x and y are independent, and this is equal to e of x, e of y. So we will show you the steps that how to calculate all those things. But in general, if x and y are not independent, then we have to compute e of xy using this result. Now, there is a concept to measure the dependency, means if x and y are not independent. Okay, so there must be some relation between x and y. So in that case, we define a term which is ultimately we will define correlation. But before that, we measure. We have another measure which is known as the covariance. Okay, so in short, this covariance between the two random variable x, y. So usually covariance is written as COV. This is the shortcut notation just for variance and expectation. So this is shortcut notation. So the covariance between the two random variable x and y are denoted by COV x comma y. So this represents the covariance x y, and it is defined as expected value of x minus ex into y minus ey. Okay, so this particular definition can be further simplified for computational ease, that it is written as, if you multiply x into y, x into e of y, ex into y, and ex ey. So having done this one, if you further simplify, ultimately you will get this result. Okay, so this is another way to compute the covariance between x and y. So it is equal to e of xy minus e of x, e of y. So one can compute this expression independently, this independently, and then the combined expression of covariance xy you will get. Otherwise, one can use this one also, but this is little complex in the sense the calculation is little more involved. But here you get a very simplified expression. Now, from here you see that one important result, that if x and y are independent. So previously we have just proved that if x and y are independent, then e of xy will be e of x into e of y. And if we substitute this here, then we get covariance 0. So if x and y are independent, then covariance xy is 0. However, the converse may not be true. Okay, means if the covariance is 0, then you cannot say that x and y are independent. Say for example, okay, so converse may not be always true. So let us take one example to demonstrate this result. Say x takes value minus 1, 0, 1, y takes value minus 1, 0, 1, and the joint probabilities are given here. Now, here I am demonstrating that how do we calculate e of xy. So as I told you, e of xy, because we have to find out the covariance of xy. Okay, so the simplified expression is there, this one. So this result we use to calculate. So we have to calculate e of xy. So e of xy, as I told you, minus 1 into 1 into 1 by 8, minus 1 into 0, 1 by 8, minus 1 into 1, 1 by 8. Like this you continue, and last value will be 1 into 1, 1 by 8. So ultimately, if you simplify this, you will get 0. So similarly, E of x, how do we calculate E of x? We know the marginal probability of x. So x takes value minus 1, 0, 1. Corresponding probabilities are 3 by 8, 2 by 8, 3 by 8. So it is coming 0. So E of y is also coming 0. So covariance equal to 0. However, if you want to see that whether x and y are independent, you have a result that the joint probabilities must be equal to the respective product of respective marginal probability. So now if you check joint probability, that x takes minus 1, y takes minus 1. Okay, p minus 1, 1 must be equal to p of x minus 1, p of y minus 1. So if you look at the table, this value is 1 by 8, p minus 1, 1, whereas p of minus for x taking minus 1, this probability is 3 by 8, and this is y taking minus value is 3 by 8. So if you substitute here, you can see that it is not equal. Okay, so in this case, even though covariance is 0, x and y are not independent. Okay, so in general, you cannot say that if x and y, if the covariance is 0, then x and y are independent. However, if x and y are independent, the covariance will be definitely 0. So in the case of the bivariate normal, I will show you the exception of this result. Is that fine? Okay. So there is another measure. Basically, it measures the relationship between the two variable x and strength of linear relationship, rather we call it. So it is known as the correlation between the two random variable x and y, and we have a notation for this rho xy. So if you are dealing with only two random variable x and y, we can use rho, but in general rho xy represents that you are dealing with two random variable x and y, and we denote it by rho xy, and it is defined as we will drop this notation xy because we are dealing with x and y. So rho is defined as covariance xy square divided by square root of variance of x, variance of y, and sometimes we use a notation for covariance as sigma xy, and square root of the variance of x is a standard deviation, so sigma x and sigma e. So this particular result is often used to calculate the correlation. As you can see that this row is independent of the unit, whereas the covariance is not independent of the units. Means if x is in minute, x is height, y is weight, then covariance unit will be there. But here all the units get cancelled, so it is independent of the unit. So the result of rho is that it lies between -1 and 1. Okay, so there is a proof for that the correlation coefficient between x and y always lies between -1 and 1. So that we will prove that result. But before that, what is the use of the covariance in case x and y are not independent? So if I have to calculate just like E of x plus y, we need to calculate what is the variance of the sum of the two random variables. Okay, what is the variance of the sum of two random variables x plus y? So as usual, you can write x plus y as z. So variance of z is expected value of z minus expected value of z whole square. So you substitute z equal to x plus y, and so ultimately you get expected value of x plus y, this expression minus this. Okay, so if I consider this as z, so this is e of z minus e of z. Okay, so I can simplify this expression. So uh, if you rearrange the term inside the bracket, this whole term, so x minus e of x, y minus e of y, and whole square. So if I open this bracket, so expected value of x minus ex whole square, expected value of y minus exy, and the product term will be there. So this product term we have defined as a covariance xy. This is variance of xy. The second term is variance of y. So there is a general expression that variance of x plus y is equal to variance of x plus variance of y plus 2 covariance xy. So if x and y are independent, then covariance will be 0. Variance of x plus y will be simply variance of x plus variance of y. So in case of the normal distribution, when we were adding the variances, there we were always making the statement that x1, x2 are independent random variable. And because of that, they are independent random variable, covariance is 0. So we use there the additive property of the normal distribution. Similarly, variance of x minus y, just like x plus y, x minus y, it is variance of x plus variance of y minus 2 covariance xy. So these are the two important results which we frequently use. Okay, so the generalization of this result is that if we have ax, a and b are two constant, so the variance of ax plus by. So plus minus means ax plus by, ax minus by. So the general result is that a square variance of x plus b square variance of y plus 2ab covariance xy. And if it is minus, so it is minus 2ab. So you can derive this result. It's not that difficult to derive, but you can remember this result that it is frequently used in many applications. So all the time you cannot derive the result. So it's better to remember this particular. So this result, as I told you, reduces in a simplified form if we put the condition that if x and y are independent. So if x and y are independent, the covariance terms will be 0. So variance of x plus variance of y, variance of x minus y will be variance of x plus variance of y. This is very important. Okay. Common mistake many people do it, that you put minus. So that is not correct. In expectation, minus will be there. And in general, for variance of ax plus minus by, a square variance of x, b square variance of x. So next thing is to show that rho lies between -1 to 1. Okay. So how to show that? There are several ways, but the simplest way I'm showing is that I consider two terms. One is variance of x divided by c sigma x, another we consider y divided by sigma y. So variance of x over sigma x plus y over sigma y, since variance is a non-negative quantity, so we use this condition. Okay, variance cannot be negative. It could be 0 or it could be greater than 0. So we use the previous result, this one. Okay, this particular result, by assuming a equal to 1 by sigma x, b equal to 1 by sigma y. So here I have written a equal to 1 by sigma x into x, 1 by sigma y into y. So this is greater or equal to 0. So now you open that. So 1 by sigma square variance of x, 1 by sigma y square variance of y, plus twice 1 over sigma x, sigma y covariance xy. This whole thing is greater than 0. Now variance of x is sigma x square, so that get cancelled. So 1. Variance of y is sigma y square. it is 1. This becomes the this inside this whole term is basically the definition of row. So 2 row, this is greater than 0. So if you simplify, you get row is greater than -1. Similarly, to prove that it is less than 1, we consider the minus expression, variance of x over sigma x minus y over sigma y. This is greater than 0. And just we follow the previous step, and you will see that rho is less than 1. So the derivation is simple here. So ultimately what we have seen that rho lies between -1 and 1. Now, in order to compute the rho from a given joint distribution, okay, so if the joint distribution is given, how to compute the value of rho? So in order to compute the rho from the joint distribution, we need to know the marginal of x, marginal of y. Once you know this, you can compute E of x square, and then variance of x. E of y square, variance of y. Then you have to compute the product, E of xy, because x and y are not independent, so we need to compute this term. Once we know this, we can compute the covariance and then find the value of rho. So one example I have shown that here the joint distribution is given. So it is very simple. So you will be given only the terms inside. So after that, you have to find out this marginal distribution, Okay, so now once we have marginal distributions for respective, we can calculate E of x square, E of y square. Then correspondingly, we can calculate variance of x, variance of y. Now, in order to compute E of xy, as I told you that you have to use this 1 into 1, 1 by 6, 1 into 2, 1 by 6. So that will give you 35 by 12. So having done that, we need to compute variance of x, variance of y, and the covariance term, because you have calculated E of xy here, E and variance of x is 5 by expected value of x is 5 by 3 and expected value of 11 by 6. So 5 by 3, 11 by 6, and this term. So ultimately minus 5 by 36. So correlation is covariance divided by sigma x, sigma y. So since we have calculated variance of x, you take the square roots. So square root of 5 by 9, 23 by 36, and in the numerator you have covariance term, which is minus 5 by 36. So you substitute here, and if you simplify, you will get minus 0.233. So you can check the calculation. I just explained you the steps. So there are some more results we will discuss in the next class, and specifically we have to discuss that in case x and y have a joint density function, then how the corresponding theory changes. So all those things we'll discuss in the next class. Okay, it is fine. So I'm stopping at this because some of you might be having the next class. So